part in this event. So I'm going to talk about physical AI, and it is what we think about as the next wave of AI. As you all can recollect, AI started from in 2012 when with AlexNet, which you think about as the first contact, and the first applications that got transformed by AI were perception applications. We saw speech recognition, medical imaging, deep recommendation systems. But then the next wave of AI which took place was generative AI, and this is where LLMs came in, content creation, digital marketing, all of that got transformed. And then the big wave which is going on right now, which is agentic AI, where you have a bunch of these AIs working together to solve really hard problems. What you see is that with each wave of AI, the opportunity that it solves, the problems that it solves keeps increasing. The scale of AI keeps increasing. And we are on the cusp of the next big wave of AI, which is the physical AI, and where AI leaves the digital world and actually starts taking decisions and manifesting itself as autonomous vehicles or general robots. A question often I get asked is, why do we think physical AI is going to be bigger than digital AI? And the answer is pretty simple. If you look around us, what IT has done for software industry, our physical world has completely been left untouched by it. If you go to a hospital today, if you go to a manufacturing site, a factory, a retail store, or even inside our homes, we are still doing the same thing that we were doing 20 years ago. So the opportunity for AI when it comes to physical world is huge. The number of atoms in the world is way more than the number of bits. So these are trillions of dollars of industries when you look at manufacturing, when you look at logistics, when you look at retail, when you look at healthcare, which is not at all being touched by AI, and the improvements have been very incremental. And as we have seen with the IT world, when AI comes in, we get 10x, 100x improvements in what we can do with that technology. So just by first principles, the opportunity ahead of us when we bring AI into the physical world is going to be much bigger. And what exactly does separates digital AI from physical AI? So in physical AI, we think about we have sensors that are inputs. In digital AI, most of that sensor is images, videos, or text. That's about it. But the physical world has a lot more sensing modalities. We have the notion of touch. We have the notion of spatial and temporal understanding of the world. We have the notion of speech. We have a lot more senses. So the data modality itself for physical AI is different, right? So we have all these sensor inputs. And then we have, of course, an AI model that has to reason across these modalities. And at the output of it is an action. And we think about at Nvidia, physical AI will manifest itself in kind of three different forms or embodiments. The most common one that you all might be familiar with that is actually getting deployed at scale today is autonomous cars. I live in San Francisco. I go to the city and I sit in a Waymo and it just drives me around. My commute to office at work is 99% autonomous. So we are starting to see that physical AI taking scale in autonomous vehicles. The second area that we think about for physical AI is robots. These are industrial collaborative robots that we see today, and autonomous mobile robots moving around in the logistics facilities. But the next wave of robots as well, which is going to be more collaborative, more human-like. So it could be humanoids. You saw several different robot form factors in the video that I shared earlier. So these are robots that are moving around, doing things, interacting with objects in the real world. The third physical AI system that we think of is factories and warehouses. And people ask me, like, how is a factory or a warehouse a physical AI? if you have cameras that are monitoring and taking decisions on what should be routed where, what should be the speed of the conveyor belt, it's checking the quality of your products and making decisions on, when to stop the line. All of that may not be directly doing the action, but it's taking the same thing. It's taking the sensor data from your site, making sense of it with a model, and taking action on what you should do. So, in a nutshell, you've got sensors input, you've got a model that understands that sensing inputs and take actions. And India is uniquely positioned to succeed in the physical AI and robotics world. And there are two big reasons for that. First is Nvidia, India has this natural resource of talent which comes from IT and computer science. As physical things, as manufacturing, as all of these operations become a digital problem, it all becomes a software defined problem, then the talent that has been used to build the IT infrastructure and the digital infrastructure of the world can be used to build the physical infrastructure for India. So that huge talent pool that we have from IT and computer science can be applied to physical world and transform that world. The second big reason for why India can succeed is the emerging manufacturing base. We all know there's a lot of changes that are happening in the manufacturing and the geopolitical environment. India is becoming the base of a lot of manufacturing that will be done in the future. So there's a huge opportunity from there. But India also is a big consumer. You have a big population that consumes these products. So why not build it for yourself? So combining that huge opportunity for manufacturing that is coming because of all the onshoring that's happening and local push for made in India, combined with the demand, puts another dimension to why India can succeed in robotics and physical AI. And if you combine these two things together, you have a virtuous flywheel that enables the success for India. Um, Before talking into the solutions that we are building, I want to give a little bit of overview of why physical AI is different from digital AI. LLMs have made a lot of progress and they're solving really hard problems. But when you come to the physical world, there are something that is very unique. I talked earlier about multimodality. You have data coming from LiDARs, cameras, microphones, touch, torque, IMUs. All of this modality of data is not understood by the models of today. And this data is continuous. And it's something that the models need to really understand. A human being, for example, can generate a lot more data through all its senses than all of internet in a matter of day, right? So when you think about physical AI, the multimodality becomes very important. The second challenge that is faced by physical AI is the data gap. You'll say, well, you just said there is so much data that gets generated, then what's the data gap? The data gap is for AI to learn that data needs to be digitized. You need to tokenize the data. Are we doing that today? Everything that's happening in a factory, in a retail store, or in a hospital, none of that operational data is digitized today. So we have this gap where let's assume we have a model that can learn from all of the data, but is that data available for the AI to learn? So where are we going to get the data from? The third challenge that comes with physical AI is evaluation. Because this AI is going to live in real world and actually taking actions, the amount of evaluation and rigor that you need to put into testing and validation is way different than you can do with a LLM that is, a chatbot. What's the worst that can happen with a chatbot is you don't like the answer and you say, try again. But if your surgical robot made a mistake, there's no try again. You got to do it right in the first shot. So evaluation of the AI is super important. And the last thing, which is important to understand, is the need for accelerated computing on the edge. When ChatGPT came out, it could reach millions and millions of people overnight, because for distribution, all that you needed was, access to a computer or a phone and a website, which is everywhere. But when you think about physical AI, it the AI needs to run on the device, because it has to be low latency, it has to be safe, it has to be, for security reasons, you want the AI to be running on the edge. That means we need to start building systems, we need to start building infrastructure where you have AI compute on the device to run the system models. So, these are some of the big challenges that differentiate LLMs from what we see in the physical AI world. And you know, the way we are going, the biggest, if you're working in this domain, you may have heard a lot about the data problem that I mentioned earlier. But I think we have a path forward to solve that today. We have the technology to solve that today. And how that's being solved is through what we call this the data pyramid. The first source of information that's being used to train physical AI is human videos and web data. India is playing a huge role in providing this data economy. We have, I know of partners who are creating millions and millions of hours of egocentric data, just observing people do things and learning from that. And of course, our YouTube and the videos that we have on the internet are great for general understanding of how the world around us operates. So that forms the basis, the foundation layer of how we are going to train the physical AI. But if everybody could just watch videos and learn, we would all be like Federers and Tiger, be experts at our craft and sushi chef. It turns out you need to do things in the real world to become good at it. And there we are working with simulation and synthetic data, creating highly fidelity models of the world where actually the robots, once they've learned, they can practice their craft. But that's also not enough, because as we know, anytime you try to create a model of something, you lose some fidelity, right? The real world is way more complex. The physics of the real world is way more complex. We cannot encode it all into simulation. But once you have the base layer and a model in simulation where you can learn and practice, then the last yard becomes just a few attempts on the real world. And just with a few attempts, that sim to real gap can be closed, and you can have a system that is fully performant. So with this data pyramid, we believe that we can solve the data problem, which has been a big challenge for physical AI. And we think about the transition in robotics is going to be two stages, right? First is the robots that we have today. These are specialist robots. They can use AI, but they can use AI to do only one task really well. If it's a robot that knows how to do welding, it just knows how to do welding. If a robot that knows how to do packaging, sorting, it just knows how to do sorting really well. If it's an AMR that is doing last mile delivery, it only knows that. But in order to get to the scalable solution, we need generalists. It does not make sense that every time you get a robot, you have to start from scratch and teach it what does motion mean, how do you pick up an object. It should have that basic intelligence built into it. So that's where a lot of focus is right now, is to create these pre-trained models and to create hardware that is multi-purpose. You need to have a general purpose hardware and a general purpose model that has the basic understanding. But the real unlock of all of that will happen when we have generalist specialists. So, if you had just graduates in the world and they were allowed to run the whole country, the whole manufacturing, we would not be where we are. We need specialists who know the craft, who have the domain expertise. And so taking this generalist brain and building specialist apps through your data for your own domain is where the real unlock happens. And that's where the real opportunity lives. So what's Nvidia doing to solve this problem? We build computers, and as I explained earlier, creating physical AI, deploying physical AI requires something more than what we have seen today. In the world today, for LLMs, you have a data center. That's pretty much all you need, and you need a lot of applications on top of that. You can train in that data center. You can run inference in the data center. That's great. But for physical AI, we need two more computers. We need a simulation computer where you can create data that doesn't exist, where you can have the robots practice and learn the skills that they have acquired by watching videos or by watching other egocentric data. And the third thing, computer, so that's the simulation computer where you train, test, and create data for your robots. And the third computer you need is the edge computer where your brain is going to get deployed. So at NVIDIA, we're building the NVIDIA Jetson, which is, in today, you can run 2,000 teraflops of compute on the robot brain itself. So, tens of billion parameter models, which could only be run on the cloud, can now be deployed onto the edge. So if you're attending this show here, you want to go to NVIDIA booth and see a lot of our partners actually deploying really advanced models onto the edge. So that's what we do on the computer side. We're building these three computers that will help developers to build physical AI. But that's not sufficient, right? That is, we need to build the software stack on top for the developers to actually leverage these computers. And we think about the software NVIDIA is building as fully open platform. The reason we are doing this is, as I mentioned earlier, every domain, every country, every task will require specialization. And if these models and these tools are not open, then you cannot scale the deployment of physical AI and robots. So we are making our entire platform open so developers in every region of the world can actually get access to it and build their own applications. So the core work on the software side can be bucketed into four categories. We have open models, we have frameworks and tools where developers can write their own applications. In robotics world, it turns out, in addition to AI, you need some more algorithms that are non-AI, but they still need accelerated computing. So we have a lot of those model libraries for accelerated computing, which we call it the CUDA-X libraries. They are accelerated on the GPUs. And the last piece is these workflows, right? I have a model, I have a tool. How am I going to use those to build a navigation stack, right? So we provide workflows using our libraries and tools that the developers can take as a tutorial and start building on top. I want to spend a little bit of time talking about simulation and why I feel it's super important. What you see in this picture is a variety of robots. If you went today in the market to go buy these robots, first of all, by the time you get them delivered to you, it's going to be probably a year out, right? And the second thing is you would need millions of dollars of budget to actually go buy these robots. But what we have done with simulation is in order to get access to any of these robots today, you just need a computer with a GPU and internet access, and you have access to this robot. These are $100,000 robots that is available to a developer anywhere in the world to go build applications. So simulation is not just accelerating how we build robots, but it's really democratizing the access to robotics to everybody in the world. So whether it's a mobile robot, it could be a Fanuc or a Kawasaki industrial arm, a collaborative arm from UR. The Adverb robots will be soon available here. So all these robots are available at one click in your browser. Imagine what that does for the developer ecosystem and how you build applications. So we are investing heavily in simulation to make sure that the robotics can be democratized. But in addition to being accessible and democratized, simulation is at the heart of how AI robots are getting built. We have environments where robots can learn by practicing. We call that reinforcement learning. This is we have a product called Isaac Lab. What you can do with Isaac Lab is on a single GPU, you can create 3, 4, 5,000 copies of the same robot and let them learn and practice by themselves. Imagine if you had to do that in the physical world. it literally brings the cost of development down to zero for AI, for robotics. And also, what it does is the time it takes to build applications reduces. So when you're doing robot learning, you would have to take years and years of data in the real world, which can now be compressed into minutes and hours, and you can have policies that can be deployed. The second thing you can do with simulation is create synthetic data. You know, you can have 3D assets of the environment where you want to deploy your robot, and you can create variations of it. You want a wooden version of it, marble version of it, metal version of it. All of that can be created just by programming and creating more data sets. An important thing for robots is testing. You need to be able to test them at scale. So instead of having to have hundreds of robots and breaking them and putting things at risk and safety hazard, you can test your entire robotic stack into simulator. So any robot that you see out today, if you are into robotics, you may have seen all these videos of humanoids doing amazing things, from dances to kung fu. Each and every robot that you see there today that's doing those skills has learned it in a simulator that's powered by Nvidia. There is a huge opportunity there to really jumpstart and accelerate the development of robotics through simulation. So with Isaac Sim, which is a tool for where you can create environments, test your robots, to Isaac Lab, where you can scale them out and let them learn on their own, the time from thinking about a problem and solving it has dramatically reduced in the world of robotics. One of the important models that we are building is called Cosmos. It's a World Foundation model, and as with all other models that NVIDIA builds, it's open source. Not just the model weights are open source, but the scripts for fine-tuning that model is open sourced. Not just the scripts are open source, the data set that we use for creating these models are open sourced. And why we do that is because we want to build the base layer on which everybody else can build their applications. We absolutely do not know how a manufacturing site for Tata Motors look like. We absolutely do not know, what a specific retail store in a particular region looks like. So how is it possible that we can create one model that can serve them all? Instead, what we do is we take the knowledge of the world, build it into these models called Cosmos World Foundation models, and we make it all available so you can bring your own data, fine-tune them, and customize it for your domain and application. And there are three categories of models that we have in Cosmos. One is Cosmos Predict. What it does is it takes the text and a video or an image as an input, and it has learned from seeing what happens in a typical world when somebody says something and sees something. What are the next thing that can happen? So Cosmos predicts the future based on the prompt and the current sensor data. Imagine if you had this capability running in real time. What it tells the robot is, this is what you should do. So the planning part of the robot is already done. All that you need to do is, okay, I know what should be done. The planning is done. I just need to do now the controls aspect of it. Right? So Cosmos Predict is super powerful for as a simulator, neural simulator. It's a great tool for planning purposes for the robots. Cosmos Transfer is a model that can take video in and video out. When we are collecting data, if you collect the data in a particular factory, in a particular lighting with a particular environment, you go to a different factory, there's no chance that the environment is going to be the same. So how do you take the data that was collected in one environment and multiply it so that the models can generalize it? That's where Cosmos Transfer comes in. It can take video in, and with prompts, it can generate different versions. So you can drive a car during the day, you can operate a robot in a specific lighting, collect the data, and then let the computers work on it to augment the data. From that one day driving, it'll create 6 variations or hundreds of variations of it in different environments. And now you can use that to train your model and generalize it across scenarios. The last model in this family is called Cosmos Reason. It is a video language VLM. It takes the video as input and language and a prompt as input, and it generates text as an output. I'm going to dive a little bit deeper into it in the next slides. But Cosmos Reason gives you a lot of capabilities to understand video, which encodes physics, but it also encodes spatial understanding. It also encodes temporal understanding. So it goes a lot more than standard detection and segmentation based models. So let's take a look at few use cases where Cosmos Reason, which is a video language model, is used by physical AI developers today. The first one is what we call as data curation and annotation. Earlier, I was talking about the data being captured and being tokenized so that the AI can learn. Even if you have a car that's driving around the street and collecting the data, before it can be used to train an AI model, there's a lot of work that needs to happen. First of all, you don't want all the data that the car is being collecting because that's a huge amount of data. Half of it is just things that are normal, and there is no signal in there. There is just things that the model already knows. So you want to first identify interesting segments of the data that was being collected. How are you going to do that? If you're going to have a person look at all the logs, that's super inefficient. So you can pass them to video language models like the Cosmos Reason and say, hey, why don't you just do all the annotation of whatever you saw, break down the video into 30 seconds chunks, and summarize it in text prompts. Once it's done the text prompt summarization of that video, now you can go to a LLM, choose your favorite one, whether it's Grok or Gemini or Nemotron. You can pass all this text and they say, okay, this is what happened. I'm looking for this type of events. And now the LLMs can reason about the text. They understand text. They don't have to watch the video anymore. They will just look at the text annotations, identify the relevant videos, and boom, from your petabytes of data, you have interesting data that you can use for training of the models. The second one is robot planning and reasoning. Typically, if you look at a robot software stack today, it has atomic skills: move left, go down, pick up object. So it has a set of base commands, so you say that it understands. But as a person who's controlling the robot, you cannot give it prompt in that sense. You want to say, pick up this thing and put it in that particular bin. Somebody needs to go and translate that into robot-specific language. Robot language is all text. So what do? You give it a prompt, you give it a video, and it generates the step-by-step instructions now that robot understands. So it gives it in language that the robot understands, and it can do the task. Another big area where we have a lot of partners who are using Cosmos Reason, and you can see sort of these applications at the Nvidia booth, is in what we call video analytics. So you've seen a lot of cameras mounted at intersections, inside facilities for security, safety reasons. But they've been their ability has been very limited because all that they do today is they detect a car. That's interesting. But is it not interesting if they can detect a car that's moving at a certain speed? Or is it not interesting if they can detect a car that is going in the wrong direction? In order to do that, you need to not look at the single frame, you need to look at the video. You need to be able to understand, is it going left to right or right to left? What is the speed? So these are spatial and temporal understanding that the current detection and segmentation models lack. This is where Cosmos Reason comes in. It looks at a sequence of videos, understands it, and gives you an answer. And you can ask, hey, how many cars, went through this intersection at this particular speed, or which one this particular lane, right? That level of querying was just not possible in the past. But now with vision language action model, with VLM models, you can build these applications really easily by just text prompting it and using a pre-trained model. So the possibilities are endless. I'm just giving you some examples of where developers are using it today. But if you are working with physical AI and robotics, I highly recommend you try the Cosmos models. They're super powerful. They're all open source for you to build on top of. This is another example of how we use Cosmos. Think about training a robot. In a previous session, we were talking about how we have to grab a particular can and put it away, and it seems very non efficient if we have to do this one time with the right hand, one time with the left hand, and then move the object a little left and a little right. That's just super inefficient use of human capabilities. So what do? Well, we show it one time what it needs to be done, and then Cosmos model can reason through it and create variants of it. Now you can just prompt it. Instead of a can, you can say, hey, what if there was a cup here? Can you generate the data for me? What if there was an apple here? Can you generate the data for me? So the whole theme that you will see here is that we want to reduce the effort that it takes to create these AI models. If we were limited by scale of people and time, it will take us years to build these models. We have to rely on compute. Compute is a data strategy for physical AI. Another big model that we are investing in and we are making available to developers is the Groot model. This has been trained for humanoids. And why humanoids is important is tied to my earlier explanation of what's happening in robotics. The robots of today, they are all very purpose-built, single function. But with the humanoid, we finally have a platform shift that's happening where you can have a general purpose brain and a general purpose hardware that can do multiple things. So Groot is Nvidia's vision language action model. It can take the sensor inputs from the robot as and a command from an operator of what they want the humanoid to do, and it can generate the actions for the humanoid to perform that task. Again, we are not focusing on, there was a question earlier, how do we do that in a wet lab? That's not our focus. Our focus is to make the foundation skills available in a model that you can then use to post-train it for your specific application. And we don't build robots, and we don't build even the solutions for the robots. We build the computers and the base infrastructure. And we are proud to have partners that use our technology to build applications. And we have a pretty big ecosystem of partners here in India. I want to call out a few of them. Adverb is a leading provider of warehouse and logistics solutions. They are showing the robot quadruped here, and they also have a mobile manipulator that's built with Nvidia technology that is capable of doing this generalized task, end-to-end learning capabilities. ATI makes AMRs for factory and warehouses. eInfochips is a great partner of ours. They provide services, so if you are a company that is looking to use Nvidia technology, you don't have the in-house R&D capability, you can go to eInfochips. They will build customized solutions for you. Autonomy, they're a partner that is doing, started off with last mile delivery, but they've expanded into a lot of different areas like hospitals, and their robots are unique because they can do indoor and outdoor delivery operations, which really opens up the spectrum of what you can do. Answer Robotics, they're building an interesting category of robots, which we call as mobile manipulators. These are AGVs with industrial arms on top of them. What we saw was that once an AGV and AMR takes the payload to a specific location, it used to keep waiting there forever because you need somebody to unload it. And that made the value of an AMR really less compared to if the robot could actually unload the stuff as well. So with mobile manipulators, the robot can not just move there, but actually do the unloading and loading task as well. Aura ML is it's a great startup which is investing in the area of simulation. As I told you earlier, all modern robots are trained and built and tested in simulation. And Aura ML provides the base infrastructure which can take your data, they can talk about your application and give you a simulation environment in which you can go train your models. Orangewood is creating industrial robots, and remember I was telling you about how today the robots have to be programmed in a very old language where you don't very few people know that. Orangewood is changing that. You can just talk to your robot, it'll understand what you want, break it down into tasks, break it down into a language that the robot can understand and perform that specific task. And general autonomy is building robots for developers so that we have a lot more hardware on which people can build applications. Last, but probably one of our most important partners in India are GSIs, the system integrators. Robotics is pretty complex problem. It has many parts from design to develop and then operate. And our partners here in India, EY, Infosys, TCS, Wipro, they are bridging this, serving the purpose of bringing the industries and the technology together by building customized solutions. So they're all here at the event. Highly recommend you to go and check out what they're building. So, so we talked a lot about robots, which are doing things. I want to briefly talk a little bit about factories and warehouses and how they are becoming robotics. What you see in this video is on the left is the physical robots. This is where we are. This is one of our partners' manufacturing site, and as you can see, they're using a digital twin to train these robots how to actually do the server assembly for one of NVIDIA's GPU servers. But on the right side, this is where what we call as the outside-in AI. So the first one is inside-out AI. The robot sees something, and AI helps it to understand and act on it. Outside-in AI is where you don't have actual control of something, but you are observing what the physical agents are doing. And based on that, you are making decisions, right? So this is AI observing other AI and making actions on it. And this particular example is of a forklift, which is manually driven in a warehouse. And these are cameras that are observing it, and you can ask if this forklift was doing something wrong, if there was a security hazard, if it was operating with the right efficiency or not. So all of this is now possible also with the power of physical AI models. Adding to that, we are seeing several visual AI agents that are being deployed in manufacturing today. The first one is visual inspection. Whether you are looking at a part and you want to see whether it's missing something, if the label or something is in the wrong place, it's very easily doable using AI agents today. A second thing that is happening is what we call as operator co-pilots. Imagine what happens when you have to start manufacturing a new product. You have to train your entire workforce. You have to give them a manual of how to build. But oftentimes, people take wrong steps, even with the manual. And the way they get reported is at the end of the process. It did not work. Well, you trace it back and you saw the operator did something wrong. Wouldn't it be great if there was an AI that was watching the operator at each step and told them, hey, you're doing this wrong, or you missed this particular step right when they did that? So with visual AI models and VLM models, because it can understand space and time, it can give you prompts to tell you to the co-pilot, this is the next thing you need to do, so that there is no guessing and you can have a better quality. And the last one is these higher level orchestration agents. There are a lot of things that need to be orchestrated and coordinated when you're running a manufacturing site or a factory. And with AI agents today, if you can get all the information about with the sensors of what's happening where, all this orchestration can be automated with AI as well. One blueprint that NVIDIA has built that really accelerates the workflows that I talked about earlier is called video search and summarization. Again, it's available openly. You can download this blueprint, run it in the cloud, run it on the device, and actually build applications for computer vision. You can train multiple You can send in multiple camera streams and do optical inspection, do safety and security, and do operator assistance. So all of this using this one single blueprint. So with that, I would like to conclude my talk. We have a big event coming up. I would love to open up the invitation to all of you. It's called our GPU Technology Conference. It's happening in March. Our CEO Jensen is going to be giving a keynote. So any of you who are interested in getting a glimpse of what's next for AI and the future of AI, highly recommend you all to join us for GTC. And in conclusion, again, huge thanks to all our partners who have supported us in our journey. We could not have done it alone. So thank you so much for being a part of this event and being a part of NVIDIA ecosystem. I think we have a few minutes for questions, or okay. 5 minutes? Okay, 5 minutes. Yeah. All right. It doesn't really have a mic. Do you guys have a mic?
Yeah, I think yeah, it will be audible. Yeah. Actually, the question of standardization, the question of interoperability, and the question of device or mobile, this robot identification and orchestration and fleet kind of a management. Do you support all the integrations part and suppose multiple robots from multiple vendors, multiple tech stacks, all these issues, how we are going to resolve?
I'll just repeat the question. The question was about standardization and how do you have different people, operators providing technology that can be integrated together. So that is one of the reasons we made our platform open. Right? So if you look at Isaac Sim, it supports ROS. So any ROS robot can talk to it. And we also make the APIs available. So if you don't support ROS, you can write a custom wrapper. So that's why the openness of the platform allows you to make a communication bridge. We of course support the standard things like MQTT or ROS and other interfaces, but you can extend it to your need. And the second thing we're doing is I don't know if you're familiar with OpenUSD. This is a standard that we're working with partners around the world, so that all their assets, every physical object can have a digital copy of it, which can be used for simulation, which can be used for data generation, for testing. So it's an open standard. It was started by Pixar, but Siemens, Intrinsic from Google, Foxconn, a lot of big industry players are all part of it. They're all contributing to it so that we all have a digital twin that we can use. And once you have a standard for a digital twin, then everything can be connected together to do the simulation.
Another question, what would be your plan and what you call vision for quantum and this particular physical AI possibilities and integrations?
I think quantum computing, of course, has a lot of benefits, and we are actively working with the ecosystem there to see how accelerated computing combined with quantum computing can solve some of the problems that require more compute than what is possible today. So I think there are some really hard simulation problems. If you think about simulating the entire factory at particle scale, you cannot do that with today's technology. So I think we are looking at what it can unlock further as that technology becomes available.
I wanted to ask, is current edge in compute ready to support space robotics demand if you see there as a market? Because this was all on-Earth applications.
Yes, the answer is yes. And there are jets and devices in the International Space Station today that are doing multispectral imaging. And imagine, if you're collecting all that satellite data and if you have to stream it down for insights, it's very inefficient. So we have partners that have CubeSats today that have, and who are doing a lot of analytics. the next wave is likely going to be like, this infrastructure in the cloud. Like we have infrastructure in the cloud, is going to be infrastructure in the space for AI computing. So definitely on the edge side, we have deployments right now through these CubeSats and hardened environments in which you can do analytics.
Hi, Ahmed. One question from here. I'm an investor in startups. One common question is if we have to take physical AI robotics to common use cases. For example, I'm an investor in a company that does ironing, steam ironing. We're just trying to automate that. And how do I leverage your ecosystem to do that? What cost would it take? Is there an ROI on such a project? Would love to take some guidance.
Yeah, I think we can talk about it in detail offline, but fundamentally, the technology that we're building for physical AI goes across domains, right? We don't. If you look at the Cosmos models, they have been trained on a wide variety of data sources, which includes some of what your domain is needed. But the good thing is that it can be fine tuned with your own data. So what you need is the data, and for your specific domain, and our open source models, and you can build autonomy on top of that. In terms of ROI, I think you know in- often robotics ROI is thought of in a very silo way, which kills a lot of opportunity for robotics. In the past, robotics was thought of as something that's going to improve my cost, right? It's always like I can automate this thing, and I don't need that much labor to do this, and what is my ROI for cost? But but the problems have completely changed in the last few years for manufacturing, for example. It's not about cost; it's about how quickly can I change my production line. You have new demand coming in from the customers. You have new tariffs and what require you to change how you manufacture things. It's not if you had robotics and if you had digital AI and solutions, overnight you could change how your factory operated, right? It's not a question about cost anymore. It's about speed at which you can pivot. Another aspect is quality. The product that's coming out with when you're building with robots versus if you are lot of human operations involved, the quality gets compromised, right? So the ROI is of automation, physical AI is multifaceted. It starts from how quickly you can build, what is the opportunity that you can serve, how can you improve the quality, and of course, bring down the cost along the way.
Do you make non-humanoid general purpose robots, like from a first principle perspective? The human body is humanoid because of biological constraints, right? It's not a mechanical optimum.
Yeah. So if you look at the Groot model that we have right now, we tested on a humanoid form factor because it kind of gives us all the complexities of all kind of robots into one, right? But that does not mean that it cannot be used for a specific, industrial cobots. Absolutely, yes, it can be used there.
Actually, you make here.
Yeah.
You make software side looking really good, but what's on the manufacturing side? Because there is a huge demand on the market where you are the one of the best provider for the GPU. So, are there any new things are you going to innovate or going to do to respond to the demand in the future?
Well, I think I gave you the example of Foxconn, what they're doing with our platform. We are digitizing our entire supply chain exactly for this reason. We want to, even before we break ground, we need to know what is going to be the throughput, how can we optimize and improve the efficiency of our manufacturing. So we are absolutely using all of the technology to improve our own operations as well.
Hey Amit, I'm Aryan. Can Hey Amit, I'm Aryan. I generate and sell ecocentric data, millions of hours of ecocentric data to a lot of robotics companies. Everyone is buying ecocentric data now, but there's such a big embodiment gap. You talked about a layered approach towards it, but there's still so much loss of data happening. So what do you think is the gold standard right now to get the most out of these ecocentric or any form of scalable data?
Yeah, I think the reason why researchers are pursuing egocentric data is just based on first principles, right? That in a world when we're going to have a lot of humanoids, the easiest way to bridge the sim to, the embodiment gap is to build a humanoid. And they're assuming that there will be a lot of humanoids. If you can see what's happening in the world right now, last year alone, there were, 20,000, 30,000 humanoids built, and it's going to be order of magnitude more this year. So it's clear that, if we are going to have humanoid hardware, the egocentric data, which although has some embodiment gap, is the best, closest data that can be scaled for learning purposes. Yeah, we can talk offline. Yeah, I have a lot of ideas about that.
One short question. Okay, Amit, great presentation. My question is, you talked about democratizing AI, but look at how you have Nvidia Cosmos. You already had Omniverse. And you're talking about ISAC platform. Are we creating an ecosystem which was like what Microsoft did 30 years ago, and everybody started using Microsoft Windows, and that was it? So, and I'm part of one of your strategic partners. We are really looking at, when we do this upskilling, how much of general training is needed, how much of physics is needed, how much of NVIDIA specific thing is getting into the blood here.
Yeah, I think when I say democratize, I mean that all of these things are available to every developer, right? So why did NVIDIA have to build it? Because nobody else is building it. And we see that this is a critical infrastructure that needs to be created so that the developers can build applications. There's no doubt in my mind that developers won't be programming computers anymore. They won't be writing code for computers. Everybody's going to be writing code for robots, and they can be of different forms, right? It could be a digital robot or a physical robot, but in the future we're going to be writing applications all for robots, and in order to do that, you need these base capabilities. So our mission is to make it available, make it open source, and if somebody else is doing something, we are more than happy to build on top. I think time is up. I'm sorry. Yeah. I'll be around for a little bit. Yeah.
Thank you so much.
Those who want to exit, please exit from this gate.
Thank you so much. It's a pleasure meeting. Thank you so much.